So first of all, I would like to thank the organizers for the kind invitation. It's a pleasure to attend this workshop. It would have been even greater to be with you all at ECT Star. But it's a great opportunity, and I'm happy to be able to tell you a bit about some recent work on the heavy quark potential from classical statistical real-time lattice simulations. And as we've seen at this workshop, the many very interesting contributions over the past days, heavy quarks and heavy quarkonia allow us to probe different regions of a heavy ion collision from the earliest stages, from the strong field plasma region over the locally thermalized and hydrodynamically expanding quark-gluon plasma phase towards even the late stages where we were close to hadronization, because the life cycle of a heavy QQ bar pair and a heavy quarkonium state aligns, of course, with these stages of a heavy ion collision. And today we've already heard about how, for example, lattice QCD can tell us, conventional lattice QCD can tell us something about the properties of equilibrium heavy quarkonium, which is relevant for the late stages of the collision. For example, about the extraction of the heavy quark potential from conventional lattice QCD simulations. Johannes showed us some new results there, and about the extraction of, for example, thermal spectral properties from the lattice with work, for example, from Rasmus Lars. And then we had another talk by Peter, who told us about one of the approaches that are currently being developed to treat the real-time evolution of heavy quarkonium in a local thermal equilibrium, where the community has really made progress over the last years to go beyond the static picture of Matsuya and Satz, where now these open quantum systems approaches I think are really interesting and allow us to connect really first principles finally to the phenomenological modeling, somehow erasing at some point the distinction between phenomenology and theory there. And this is quite exciting. And what I would like to take the advantage of in the next few minutes is to talk about first steps that we are trying to take to eventually get a better understanding of heavy quarkonium in the early stages of a heavy ion collision, especially the formation process, which would be a probe of the strong field QCD and decidedly non-equilibrium dynamics. And to be able to do that, we will have to somehow work towards a theory description simulation of real-time lattice simulations for highly occupied gluons and heavy quarks. And I would like to tell you some news from what we've been doing in this direction. We're not yet out of equilibrium, but we're on our way. Okay, so this is what I'm going to focus on. I would like to use lattice methodology because it allows us to look at non-perturbatively strongly correlated systems. As you know, in a lattice discretization, our gauge fields are represented by these link variables that live between the individual nodes of our space-time grid. In modern conventional simulation, you have different flavors of light fermions that live on the nodes. And if you want to include heavy fermions, you can either do this by formulating them relativistically, then they share the same grid as all the light degrees of freedom, and you have to make your grid very fine to resolve all the degrees of freedom. Or you can relax this a bit and do a standard lattice simulation for the light gluons and light quarks, and then formulate the physics of your heavy quarks as an effective field theory in the background of these light fields. And there's essentially two phases of lattice QCD. The one that you're all familiar with is your conventional Euclidean quantum lattice QCD. It's formulated in a compact imaginary time, which allows us to do actual Monte Carlo simulations of the quantum path integral by drawing different realizations of the field configurations and then computing the observables of interest on those. You take the mean and you get an ab initio estimation of this expectation value. The difficulty here is this only works for thermal equilibrium, and if you want to return to the real-time domain, this becomes very costly starting off from this imaginary time. Then there's a second phase of lattice QCD, which is these so-called real-time classical statistical simulations, which are directly formulated in Minkowski time. But here, the price to pay is that you have to neglect all the quantum fluctuations of your theory. And what it boils down to is essentially that you're evolving an ensemble of gauge fields according to the deterministic Yang-Mills classical equations of motions, starting off from a set of random thermal initial conditions. At some point t, you compute the observable for each of these trajectories, and you do an ensemble average, and by that you estimate the statistical expectation value of your observable. This approach is valid at high gluon occupancy, which accidentally, coincidentally, is what is present in the early stages of a heavy ion collision, as we believe, in the Glasma phase. Or you can use it deep in the infrared, where it has been deployed to investigate topological transitions, for example, so-called Sphellaron transitions. Here, you're directly working in real time, but of course, there's no free lunch. So here, the continuum limit is an intricate question, and you would not expect to really find confinement physics. So if we want to eventually evolve heavy quarks in such kind of a scenario, it would have to be only very heavy, say a bottomonium quark anti-quark pair, because that would anyway sit in the Coulombic part of the Cornell potential, and we could get some insight here from these real-time classical simulations, I believe. So now I would like to start with the simplest possible system. This is not yet quarkonium. We are really talking about static heavy color sources, and that's the simplest system that we can think of. And we want to, and if we want to describe these heavy color sources evolving in time, we can look at the Wilson loop, which is a gluonic quantity that lives along the rectangular path that your quark, this infinitely heavy color source, traces out as they evolve in real time. And when I talk about the heavy quark or the static quark potential, then what I mean by this is that I want to know whether I can describe the evolution of these infinitely heavy color sources by a Schrödinger-like equation, meaning that the evolution equation of the Wilson loop can be written as such kind of equation where you have a time-independent potential V of R multiplying the Wilson loop on the right-hand side. That is, I want to establish whether that is possible. In general, we know that such a description is not true. There are usually non-potential effects, especially if you think about the interaction between the heavy quark and the gluons. This is a retarded quantum field theoretical interaction. So if you don't do any type of time course graining, you cannot expect these interactions to be easily replaced by a instantaneous interaction potential. But if you do coarse graining in time, you might have a chance, as our colleagues using weak coupling methods have shown us. If this potential exists, the question then is, how do I extract it from lattice simulations? And here I would like to refer to spectral functions, which at this point are just a technical tool for us. Essentially, what is the trick? Well, if such a potential exists that describes the Wilson loop, then we can use the equation of motion of the Wilson loop to define what that potential means. Namely, I can just divide by the Wilson loop on the right-hand side and look at the derivative of the Wilson loop divided by the Wilson loop at very late times. Then this function V should eventually become time independent if a potential picture is applicable. And often it is convenient to go over to the Fourier transform of the real-time Wilson loop, which is this famous spectral function. And if you plug this in, if you plug the definition of the Fourier transform in here, you can now relate the value of the potential directly to the spectral function via such kind of a ratio of Fourier transforms. Well, you can say, do I really have to compute all these Fourier transforms, or would it be possible to read off the values of the potential directly from that spectral function if I had access to it? And I would like to spend a few minutes in going through the derivation of the state-of-the-art way how we identify the potential from a spectral function. So the point that I would like to emphasize is that this the way that we have first shown here and argued for in 2012 is a truly non-perturbative argument, and it is based on two facts that you can derive from QCD. The first one is that the most general equation of motion for the Wilson loop is the one that you see here on the left. The time derivative of the Wilson loop, because it's a non-relativistic object, is just given by some complex function multiplied by the Wilson loop, and that complex function can have a dependence on r and t. And the Wilson loop, if you flip the time component, it just turns into its complex conjugate. So these are non-perturbative relations that you can establish. Now, if a potential description is applicable after some coarse graining over a time period tau pot, then this function capital phi has to become time independent after that time period. That is, if the potential exists, that is what it means. And indeed, now let us assume that the potential picture exists. Then we can always write the time evolution of the Wilson loop in this form. We say it is on the right-hand side, we now have the v of r that is time independent plus some function small phi, and that is just the capital phi minus the potential. And so this will be a function, this small phi will be a function that goes to 0 for times larger than tau potential. Okay, what does this give us? Well, in this form, we can actually solve this equation for the Wilson loop by exponentiating it. And what we get is the following expression, as you would have expected. Well, you have a time-independent component v of r that just exponentiates times t if you integrate this up. And then you have this function sigma, which is nothing but the integral over your function small phi. You have the imaginary part of the potential and the imaginary part of the sigma function, all in your exponentiated solution for the Wilson loop. Again, this is non-perturbative. And note that this function sigma, because your small phi eventually becomes 0, this function sigma also becomes constant at some point if you make your time, if you take its time argument larger than this characteristic timescale tau pot. And what this tells us is that the Wilson loop that you compute, say from a lattice simulation, a real-time lattice simulation, contains both the physics of the potential and the non-potential physics. And now we have to figure out how to disentangle those two. And here is where the spectral function really comes in handy, because let's see, that is that's the solution, the formal solution of the equation of motion that we got. And now I told you that the spectral function is just the Fourier transform of this Wilson loop. So let's take the Fourier transform. Okay, there's an omega, e to the I omega t in here. And the only thing that we've done here is that we have exploited this extra bit of information that we know that if you take t to minus t, the Wilson loop has to go over to its complex conjugate. And that allows us to actually assign explicit changes of signs to some of these terms, depending on whether t is positive or negative. Okay, so this is this is a completely general expression here under the assumption that the potential picture exists. Now we can exploit that this function sigma here becomes eventually time independent if you take its time argument to very late times, larger than tau pot. And that allows you to decompose this expression for the spectral function here into two terms. One term you have where the integral extends from minus infinity to infinity. And this is the first line here. And this one depends only on time independent quantities. The real part of this potential, the imaginary part of the potential. And here there is two remnants of this non-potential physics that is hiding in the spectral function of the Wilson loop. And then there's another contribution that goes from minus tau pot to tau pot here. And this contains all the time dependence along this interval. And the first line, the integral that spans from -infinity to infinity, you can immediately write down. And what this does is it gives you a skewed Breit-Wigner peak around the central value, and the central value of that peak is given by the real part of the potential. And you can already see from the form here that the imaginary part is related to the width of this skewed Breit-Wigner peak. And then the second line above, actually now we have no explicit expression for this, but it doesn't seem to contain an additional pole. So we just expand it around the in a Taylor series around the peak, the central peak position of this skewed Breit-Wigner, and that gives you essentially a polynomial background in which your potential peak is embedded. Okay, so from very generic properties of the Wilson loop and the assumption that the potential picture exists, we get this analytic form for the spectral function of the Wilson loop. There should be at least one dominant peak at low frequencies that encodes the potential. And if you now take this and plug it back into the spectral decomposition of the Wilson loop and how we related it to the potential, then there follows a simple recipe, namely that the position of this skewed Breit-Wigner peak gives you the real part, and the width indeed gives you the imaginary part, because the only thing that counts is the skewed Breit-Wigner with the pole that it contains. Now, if you have, say, from a real-time lattice simulation, you computed a spectral function, and you now want to extract the potential, you have to fit it. And what we've shown in mock data tests for, using hard-thermal loop perturbation theory is that if you neglect the skewing, it might seem like a small effect, but it usually leads to the overestimation of the true value of the real part. So this skewing is really something subtle that you need to keep in mind when fitting your spectral functions to get the values of the potential. The other thing is that we've tried also to look for different shapes. And one shape that immediately comes to mind is what happens if I use a Gaussian to fit, for example, my spectral function. And while the Gaussian fit ansatz, it will still lead to a real part of the potential that is somehow centered around the maximum of that peak. But the imaginary part that you would get out of this is not time independent, and therefore it is difficult to really connect such a Gaussian fit form to a time independent potential. And so far we've only managed to really derive from the properties of the Wilson loop this skewed Breit-Wigner fit form. So now this was always the forward argument. So if a potential exists, then this is how the spectral function of the Wilson loop will look like. And you can be bold, and as long as you can be sure that there are no more poles hiding in the low frequency regime below your dominant peak, as long as that is the case, if you now compute a spectral function and you find that there's a dominant peak structure at low frequencies, then that low-lying peak structure dominates the late time physics, and by that you can associate it with the physics of the potential. And we are going to use this type of recipe of how to extract the potential from the spectral function later on, when we now evaluate the spectral function in this real-time simulations. Just to set the stage, now I've told you in very much detail what is it that that we want to extract using hard-thermal loop perturbation theory. The community has shown that under certain scale hierarchies there exists a potential with a real and an imaginary part, and then we went ahead and used multiple lattice evaluations of the Wilson loop and Wilson line correlators to actually see also indications of changes in the real part and the imaginary part of a potential from conventional lattice QC. Now, what I really wanted to get at is that for quite some time there was a puzzle in the community, namely when Mikko and colleagues for the first time looked at the potential in the classical statistical computation. The first step they did is, well, they took the hard thermal loop computation in continuum perturbation theory, and they took h bar to 0. And if they did this, they got a vanishing real part. Then they went ahead and did the numerical simulation and repeated the recipe from the Euclidean side, namely evaluating the Wilson loop. And they also got only a imaginary part in the potential and no real part. And so the question is, where is the real part of the classical potential hiding? Because obviously, even if the potential might not be attractive, there's no reason why a quark and an anti-quark in a classical Yang-Mills theory shouldn't feel each other. And so to better understand what's going on, we went back and looked about what does it mean if you evaluate the Wilson loop in a path integral. And so here I write down what is the Wilson loop in a path integral. I went to spatial axial gauge. So the spatial connectors of the Wilson loop are gone, just to keep things simple. And you can see that you have one Wilson line going up for the quark at spatial x0 and one anti-quark line down going at x1. And you can put those together into one exponent. And what you will find is that this now becomes, since the A0 is involved, if you combine this into the exponential, then you get an A0 times 2 delta functions that fix the spatial component of the A0 to just the position of the quark or the infinitely heavy source and the anti-source. But this is nothing but the same expression that you would get if you're coupling a charge density, an external charge density, to your A0 field. So evaluating the Wilson loop in the quantum path integral automatically reweights a theory without static sources to a theory with static sources, and the physics of the static sources is correctly included. In classical statistical simulations, you're doing something slightly different. You're solving the Yang-Mills equations of motions. And then what was done in the literature before is simply you compute the Wilson loop in this ensemble of thermal gauge fields. And we redid this. The imaginary part of that Wilson loop is 0. And the real part of that Wilson loop decays with a nice exponential. But if you have a real-time Wilson loop that decays as a real valued function, then there's indeed only an indication for the presence of an imaginary part of a potential present. We could do our Fourier analysis. So we take the Wilson loop, we Fourier transform it, and you nicely see this skewed Breit-Wigner-like shape here. It's centered at 0. That tells you that the real part is 0, and the width of that peak increases as you make the spatial separation larger. So this tells you that you get an imaginary part that increases with spatial distance. And this looks actually quite similar to the quantum result. It increases with distance and temperature, but there's no real part. So what's going on? And we try to answer this by asking, where do the static sources actually enter in the classical theory? And the way you can write your classical statistical theory is actually in terms of a path integral that is fixed to the classical path in this delta function down here. And this is the Yang-Mills equations that's sitting inside this delta, integrated over a thermal initial conditions. But now we have to be careful, because the static sources, they have to show up in the Yang-Mills equations. And if you have a J0 there, then what does this J0 do? It modifies the Gauss law. The Gauss law simply compares the electric field at neighboring sites. You have to, in a lattice gauge here, you have to parallel transport the electric field consistently. That's why there's these parallel transporters showing up here. And in a theory without sources, that difference will always be 0. But now if you have static quarks in your system, or static sources, you will have to amend this Gauss law by this charge density that tells you where does your electric field have to have a jump as it passes over the sources that you have placed on a lattice side. And that means we have to actually use a different Gauss law, namely an appropriate Gauss law that includes the sources, to draw our initial conditions. We evolve them in time, and then we compute the Wilson loop. And if we do that, the Wilson loop looks very different. The real part of the Wilson loop now has an oscillatory and damped behavior. So does its imaginary part. And in the terms of a Fourier transform, the oscillatory part already tells you, oh, this will be a peak at a finite frequency. And indeed, if we now do the Fourier transform, you can see curves here of different colors. The larger the spatial separation, the lighter the color, and you can see that this peak now becomes broader, and it shifts with different separation distance. And lo and behold, if we now look at the position of this skewed Lorentzian peak, we get a finite value for the real part of the potential, and that is nicely described by a Debye-screened form where the Debye mass is actually even compatible with the one you get from lattice perturbation theory. The imaginary part in the presence of the back reaction we find is very similar to the one without back reaction. But now we actually have located how we have to formulate this classical statistical theory to correctly take into account the back reaction of the static quarks. And I think I'm out of time. If I may, one more slide.
Yeah, you still have a few minutes.
Okay, very good. Great. So because the next step, if we ever want to get to quarkonia, surely static sources are great, but in the end, we have to deal with heavy quarks that have a finite mass. And here we are taking the first steps towards implementing non-relativistic QCD in real time, where the heavy quarks are described in terms of Pauli spinors. The Hamiltonian, this is a systematic expansion in the heavy quark velocity. So, for example, up to order v to the third, the Hamiltonian for your quark degree of freedom has the standard non-relativistic kinetic term, a spin-dependent term, and higher order terms. And because the heavy quarks cannot be spontaneously pair created, this makes your theory much simpler, because if you want to know about the heavy quarkonium propagation and its spectral function, then usually you would have to compute the retarded propagator, which is actually a commutator of meson-meson operators. But here, because the quark pair cannot be spontaneously created, it becomes of a much simpler form, where essentially you have to just combine the propagation of a heavy quark in time forward and the propagation of a heavy anti-quark in time forward. And we need to reliably compute the heavy quark and anti-quark motion, and we do that by solving the equation of motion for the single heavy quark propagator using the Crank-Nicholson scheme. And once you plug all this in, you can now because this happens now in real time under the classical statistical approximation, you can now compute the spectral function from the Fourier transform of this retarded propagator. And since, however, you only have a finite amount of time in this real time, it's an initial value problem. So you start from some time, you evolve forward, you have only that amount of time to do your transform. So here you have to do the Wigner transform in the relative time coordinates s t1 minus t2. The first thing that we have done so far is to focus on the system without back reaction, just to see whether we can get some sense of this real-time NRQCD going. And here I show you some computations of this the non-back reaction real-time NRQCD. In the top right panel, we show the initial spectral function that you get for the singlet and octet. They both look the same, and they look like the free spectral function. So the Q and Q bar pair was just put in your system. It didn't yet have time to interact, and therefore it doesn't know of each other. So it really looks like a free theory. And then you let it evolve over time. And what we see in this very crude model here is that the amplitude for the singlet gets reduced after 100 steps in time, and the amplitude for the octet gets increased. And we interpret this as a manifestation of gluon absorption that drives our system towards more octet contribution than singlet contribution. And the next step, of course, is to implement the back reaction of that Q-cube pair onto the gauge fields. And then we will hope that this spectral function will eventually show signs of binding. And with that, I would like to summarize. I hope to have been able to show you that based on very generic properties of the Wilson loop, we can establish non-perturbatively that its spectral function exhibits a skewed Breit-Wigner peak if the potential is actually viable at late times. The treatment of static sources in the path integral, in the classical, so in the quantum path integral and in the classical statistical approximation is very different. In the former, it is really a reweighting of a theory to a theory with the sources, versus in the classical statistical approximation, we have to take care of the modified Gauss law by hand. And this helped us by incorporating the proper Gauss law into the initial conditions to really recover for the first time the screened real part of the potential in these real-time classical statistical lattice QCD simulations, which were still in thermal equilibrium. But this was a first step to get under control how we describe heavy quarks in this scenario. And now we have to really work on implementing finite mass heavy quarks in real-time NRQCD, and this is work together with Rasmus Larsen that we are now conducting. And with that, I thank you for your attention.
Thank you very much for very nice pedagogical talk. Now, please, questions from our audience. Firstly, okay, till people are thinking, I see here the hand from Ralph. Yes, Ralph, please go ahead.
Thanks. Yeah, hi, Alexander. Thanks for the very informative talk. So I wanted to come back to the issue of non-potential interactions or contributions in the spectral function that you emphasize. So I think it is important to distinguish two types. In particular, two types of energy that are energy variables that we have. One is the energy variable of the propagating pair, what you call omega, and then there's the energy variable that in principle you can exchange between the two quarks. So that would be sort of, that's a relative energy, not the total energy, in other words. So that relative energy, that is usually what is neglected when you say potential. That's usually the common term if you talk about reductions of a Bezold beta equation. And for heavy quarks, there's simply a very good reason that that is small, because the kinetic energy of heavy quarks is small, and then the energy exchange will always be much smaller than the momentum of the quarks, because it's simply p squared over 2m. That's just a side remark. My main my question was about the skewed Breit-Wigner that I talked about, and I couldn't agree with that more. In fact, I would even go one step further and say that in principle you have even more than that if you include explicit self-energies of the individual heavy quarks into your denominator, which acquire an energy dependence, because they can have a non-trivial many body structures like zero modes and all that, which would not necessarily, I think, as far as I understand, included in the skewed Breit-Wigner.
So that could be maybe a difference between looking at an actual Quark-Gluon state and these these static sources, because the Wilson loop, its evolution equation, that should always have this phi, this very simple form that the time derivative is just a complex function times the Wilson loop itself, and that's all there is. So there shouldn't be anything additional coming into this equation of motion. But if you have an actual finite mass Quark-Gluon state, then yes, I think then you might have extra contributions in the equation of motion for the propagator. Is that what you were?
I'm not sure, because I'm not talking about momentum. So infinite quark mass, you don't have momentum; it's static basically. Yes. That's fine. I'm talking about the energy dependence that you also write. That you that in a way is also this you have the energy denominator omega square minus something, right? And there should be, when you propagate that two-body state, you do have the interactions of the individual quarks, static or not, with the medium, and those self-energies can acquire energy dependencies, not momentum. That of course too, once they are finite mass, but in particular also energy dependencies.
I would have to think more about how this would potentially modify this expression.
Okay, good. Thank you.
Okay, thank you. Some other questions from our audience? I don't see hands, so I also don't see hands in Zoom participants. So, Alexander, thanks a lot.